Let us see an example. So I'm going to apply substitution method to solve this. So first I'll try to find t of n minus 1 from t of n. Let us substitute n is equal to n minus 1 in equation 1. That becomes t of n minus 2 plus 1. Now substitute t of n minus 1 in equation 1. That leads to new t of n, that is t of n minus 2 plus 2. This is equation number 2. Now find t of n minus 2. That is, substitute n is equal to n minus 2 in equation 1. So that leads to t of n minus 3 plus 1. Now substitute t of n minus 2 in equation number 2. So t of n is t of n minus 3 plus 3. Observe the equations 1, 2, and 3. So try to find a pattern. That is, after k steps, how t of n will look like. So after k steps, t of n will look like t of n minus k plus k. So this is the pattern in which the equation looks after k steps. So we assume the initial condition or the base condition as t of 0 equal to 1. So this is the initial condition. So now I map t of n minus k equal to 0. That is n minus k equal to 0. So from this, I'll try to find what is k. K is equal to n. Okay, now substitute this in equation number A. That is t of n is equal to t of n minus k is 0 and k is. So according to the initial condition, t of 0 is 1. That is 1 plus n. This is equal to big O of n of big theta of n. So this is the corresponding time complexity of the given recurrence relation. The given recurrence relation corresponds to finding factorial of a number using recursion. So here we see if the value of n equal to 0 or n equal to 1, it will return 1. So this is what we have taken as the initial condition. So here we are having two initial conditions, that is n can be 0 or 1. We are taking the least value. That's what we are saying, like t of 0 is equal to 1 as the initial condition. And we have the recursive call, fact of n minus 1 star n. So this is, for example, if you want to find 5 factorial, you can say it is 4 factorial star 5. And further, 4 factorial is when it's called as 3 factorial star 4. 3 factorial is given as 2 factorial 2 given as star. So this is what, this is how it is written here. So this corresponds to t of n, fact of n minus 1. This corresponds to t of n minus 1. And the basic operation which is happening is multiplication. And this is happening outside the recursive call. And this is a constant. So this is what we have written as plus 1. Or it can be represented as any other variables like a, b, or c. It corresponds to the constant. Let's see another example. T of n equal to 2, t n by 2 plus n. This is an example recurrence relation for merge sort. So we have to find T of n by 2. So substitute n equal to n by 2 in equation 1. That will be 2 n by 4 plus n by 2. Now substitute T of n by 2 in equation 1. T of n becomes now find T of n by 4 by substituting n is equal to n by 4 in equation 1. Now substitute T of n by 4 in equation 2. Observe the equations 1, 2, and 3 and write the common representation in terms of k. That is, after k steps, T of n will look in this form. So we have it is the equation 1 is represented as 2, then it is 4, is 8. It is T of n by 2, T of n by 4, T of n by 8. So try to find a pattern here. So the pattern is can be 2 power k. When k is 1, we get like T of n by 2 power k. Here the pattern is 2 power k T of n by 2 power k plus and the cast outside recursion. It is of the form n, then 2n, 3n. So we have to find a pattern out of this. Need to find it can be written as look for a pattern. I'm seeing like a pattern is when n is equal to 1, I'm having like this. When it is 2, it is 2n, it is 3. I can say like kn. When I substitute k, you can take this equation, general equation, represented in terms of k, substitute k is equal to 1. If you substitute k equal to 1, you will get the equation number 1. If you substitute k is equal to 2, you will get equation number 2. Similarly, if you substitute k is equal to 3, 30. So this is the correct form of it. Now you have to apply the initial condition. So here, the initial condition in merge sort, the initial condition is T of 1 is equal to 1. This is the initial condition. Then I'll be mapping the term n by 2k to 1. Okay, this term I'll be mapping to 1. N by 2 bar k equal to 1. So this can be written as n is equal to 2 bar k. So take log on both sides to find the value of k. So if I take log on both the sides, it is k is equal to log n. So now substitute in equation A. The equation A becomes t of n equal to, so in the place of 2 bar k, I write it as n. Then t of 1 plus, in the place of k, it is written as log n, then n. So like t of 1 is 1, that is the initial condition. So this is given as n plus n log n. Okay, so in asymptotic notation, we always give the priority to the highest order or the highest polynomial order. It is big omega or big O and log n. This is the complexity of the given recurrence relation, which is meant for sort.